Servo mechanisms, also called servo systems or just servos, have countless applications in aircraft and automation systems. To help you understand the big picture, I will start by giving a very brief overview of a typical DC servo system. A detailed description of the main sections of a servo system will be given later in this tutorial. The primary purpose of a position servo system is to control the position of the load it is driving. The load in this illustration is in the upper right corner of the video and could be almost anything: an aircraft control system, a weapon system or cooling door, etc. I have added 8 test points labeled TP1 through TP8 to help make the circuit analysis easier. In this circuit, the load is moved by a DC motor. In aircraft systems, the load could be moved by AC motors, hydraulic actuators, or pneumatic actuators. This particular motor is powered by a variable negative or positive voltage developed across the input potentiometer. The signal developed across the input potentiometer is sometimes called a demand signal or a command signal. A negative 12 volt source is connected to the left side of the potentiometer, and a positive 12 volt source is connected to the right side of the potentiometer. Right now, the wiper is halfway between the positive and negative voltage sources, so the voltage developed across the potentiometer is 0 volts. This 0 volt signal is applied to TP2. Now watch the wiper of the input potentiometer. I'm going to rotate the wiper counterclockwise 45 degrees. Because the wiper is halfway between the 0 volt position and the negative 12 volt supply, a negative 6 volt demand signal will be developed across the input potentiometer and applied to TP2, which is the input of the error detector. The error detector consists of 2 1000 ohm resistors. For reasons that I will explain later, the output of the error detector, which is TP3, will be about 1/2 of the input. In this case, we applied negative 6 volts to the input of the error detector, so the output will be negative 3 volts. This negative 3 volt output is called the error signal. The error signal is applied to the input of the amplifier. Again, the negative 3 volt error signal is applied to the input of the amplifier. This amplifier has a gain of about 25, so the output in this case would theoretically be negative 75 volts. I arrived at this value by multiplying the gain of the amplifier, in this case 25, by the input voltage of the error signal, in this case negative 3 volts. In reality, this amplifier is limited to an output range of negative 12 to positive 12 volts. So in this case, the negative 3 volt input signal will result in a negative 12 volt output signal. The negative 12 volts from the amplifier is applied across the motor. As you will see in a moment, this will cause the motor to turn clockwise. Because this motor is connected through a gear train to the load and feedback potentiometer, they will also turn. Now watch the load and the feedback potentiometer. Both will rotate clockwise 45 degrees and stop. Look at the feedback potentiometer. A positive 12 volt source is connected to the left side of the potentiometer, and a negative 12 volt source is connected to the right side of the potentiometer. The feedback potentiometer is wired exactly the opposite of the input potentiometer. Because the wiper of the feedback potentiometer is halfway between the 0 volt position and the positive 12 volt supply, positive 6 volts will be developed at the wiper of the feedback potentiometer and applied to TP7. The positive 6 volts will also be present at TP8, which is the input of the error detector. Look at the error detector. Negative 6 volts from the input potentiometer is present at TP2, and positive 6 volts from the feedback potentiometer is present at TP8. Because equal and opposite voltages are applied across 2 resistors of equal value, the voltage at TP3, or the summing point, will be 0 volts. With 0 volts applied to the amplifier's input, the output will also be 0 volts and the motor will stop turning. It is important to understand that the motor stopped turning only when the feedback potentiometer's voltage was equal and opposite the input potentiometers. In this case, the negative 6 volt input at TP2 was matched by a positive 6 volt feedback signal at TP8. If you don't understand this concept, don't worry. Later in this tutorial, I will cover potentiometers and voltage dividers. Before we proceed to the next section, let's recenter the load. Watch the wiper of the input potentiometer. I'm going to rotate the wiper counterclockwise to the original 0-degree position. Because the wiper is halfway between the negative 12 volt supply and the positive 12 volt supply, 0 volts will be applied to TP2. With 0 volts applied to TP2 and positive 6 volts applied to TP8, the error signal at TP3 will be 3 volts. The positive 3 volt error signal at TP3 will be amplified and become positive 12 volts at TP5 and TP6. Now watch the motor. The positive 12 volts will cause the motor to turn counterclockwise and recenter the load and the feedback potentiometer. Because the feedback potentiometer's wiper is centered, the voltage signal at TP7 and TP8 is 0 volts. With 0 volts applied to TP2 and 0 volts applied to TP8, the output of the error detector at TP3 will be 0 volts. Likewise, the output of the amplifier will be 0, which will be applied at TP5 and TP6. The servo motor will not move from this position until a position difference exists between the input and feedback signal.